So the first part of part C is to connect the interior to the exterior. So we're gonna do. It may not work for the version that I did. I'll show you how to fix it in case it doesn't work for me, so that in case it doesn't work for you, you can follow my steps. But it's a very simple maneuver to get it to do what we want to do. So, but the description of that is we return to the initial model of the rectangular polyhedron inside of the irregular polyhedron that we created in part A, and in parentheses before any scaling of the rectangular polyhedron. So if you happen to scale down your cube to get part B to work, we want to go back to the version that was not scaled down, right? So we want the gray solid that came from part A, and the original box that should measure exactly 20 by 30 by 40, right? We don't want the scaled down version of that. So I'll be working with these three. Copy over here. Okay. Let's be working with these three things here. Okay. There should be at least two faces of the inner rectangular polyhedron, so the original box, on which all four edges are fully intersected with the outer irregular polyhedron. So that would be part A. So what that means, if I go back over here, there should be at least two faces where each of these edges touches the outer geometry, right? So if I look at this one here, it looks like it's my top face and my bottom face, right? So if I look at the original box and I rotate around, I can see that this edge touches the gray box, or the gray object. I can see that this edge touches the gray object. I can see this edge touches the gray object, and I can see this edge touches the gray object. And since that's since it's a box that I could mirror in that plane, I know it's the top and the bottom.
On the sides, can you pinpoint where it doesn't touch?
Yeah, right here. This edge right here, going up and down,
okay, got it.
See that right here? That does not touch the outer shape, right? So it would just be that point where the outer polyhedron is in the same location as the inner polyhedron. And with this process, there should be at least two faces that do that. Okay? So now that I've defined those, use one of the rectangular faces to split the outer polyhedron, then mirror the split piece across that face and rejoin to the irregular polyhedron. So what I want to do is, for my example, for my situation, that's the top plane and the bottom plane of the red cube. I want to use those surfaces to split this into two pieces. Everything basically on this side of the plane and everything on that side of the plane. After I do that split, I'm going to mirror it and then rejoin it back to its original. So I think the easiest way to do that, and I'll show you what it looks like, is I'm going to select the inner box, and I'm going to type explode. So now instead of a box, I've got 6 faces. And to make sure that I trim everything the way that I want to trim it, I'm going to select this top face, right? And that's going to be the one that I use to split everything that's above that. And to ensure a 100% clean split with no errors, I'm going to scale this face larger a little bit, just so that 100% of the sectional condition between this plane and this gray object is captured by the bounds of that plane. They are touching, right? We could say, oh yeah, they're touching, it'll work. It might not. Sometimes I honestly have no idea why. Sometimes it won't work, okay? So I'm gonna scale this from the center. So I'll give it area centroid, and I will scale it from that point. I'll make it just a little bit bigger, maybe 110%, right? So now I really know that everything that I'm going to split is 100% inside the boundary of that plane. Do you see that?
So the scale is you have to. Right?
You don't have to. I recommend it. Doing this can also translate to how you trim certain objects. We're going to split this. This same method can work for trimming or capping or joining. Same sort of thought process of let me make sure I have enough material to work with so that I know that the operation is going to work, right? It's digital, you shouldn't, but I think that way, and it helps me. So I'm another pro tip, right? So I'm going to use the split command. Okay, and it says select objects to split. That's the gray one. So I'm going to split that into 2 pieces. And then it says select cutting objects. Well, that'll be this plane right here. So now I should have this piece and this piece. And they were split exactly at that plane that was defined to be, completely tangent with the inner box. Okay? Okay. So now I need to mirror that top piece about the plane that I used to split. So instead of it being a convex piece, it'll be a concave piece. And for this orientation, I'm going to use the mirror command. You'll use the mirror command in any point. However, the way that the mirror command works is it's asking me for a mirror plane, but I'm only going to be able to define a line in the XY. So, for example, if I can only define a line that's supposed to mean a mirror plane, if I draw it this way, it's going to mirror it there. If I draw it here, it's going to mirror it there. I sort of want to mirror it about itself so that in this orientation, I need to enable the 3-point sub option. So when I click that, I'm going to define 3 points of the plane that I would want this to mirror about. So you can think of that red splitting plane literally as a mirror. And we're going to define that with 3 points. I'll click here, I'll click here, and then I will click there. And now, let's say, get rid of that. Now what I have is everything that was, it was coming up this way, now it's mirrored into the object itself. I can move that around, you can sort of see it, right? And then after mirroring it, I'm going to join it back to the outer surface. And then I'm going to repeat it for the bottom. Okay? So I'll take this bottom plane, give it center, scale it from the center, a little bit bigger. Actually, I'll not do that, just to see if it does work. So instead of scaling it, I'll just skip straight to the split command. This is the object I want to split. This is the plane I want to do the splitting. And it worked just fine. So my caution was unwarranted. So now I'll do the same thing I did for the top. I will mirror that split piece about that splitting plane so that it ends up being concave into the surface itself. So mirror, I'm going to use 3-point. I'm going to define 3 corners of that plane, which should be 1, 2, and 3. Now what I have is the same condition on the bottom part of my object. Okay. And then again, I will join it back to the original polysurface. Everyone okay with that part? Okay. The next part, let me get rid of these, I don't need them anymore. Now, if I turn this back on, because I have flipped those faces in on themselves, that means that the outside is now coming out, or the inside is now coming out of the outside because the faces are now mirrored. And what I want to do is really use the outside to trim the inside, and then use the inside to trim the outside. So that after I do that, I should have a hole that starts where this object comes outside. It will go through, be expressed as the interior of the interior object, and then the other side of the hole will be where the other side of that object comes out from the bottom, right? So we're making, I don't know, a geometric donut, right? However, so I'm going to do that, but in my case right here, I have tiny portions of that interior object that are coming outside where I don't want them to. So for this step, if you're really careful, you shouldn't have that condition. However, if you do, you should scale down the interior first by a little bit, 4%, 5%, something really small. So that the only part of the interior that's coming outside are those faces that you mirrored, okay? And what I need to do is need to bring this box back since I deleted it. I'm going to use the volume centroid of this box to scale this down. So I'll scale it from that point. Let's do 0.95. Oh, that's good. Yeah, that's all right. So in the previous class, I had trimming issues, but if I encounter that again, I'll show you the troubleshooting methods that I'm going to go through in case this doesn't work for me. Okay. So first, I'm just going to try to trim it. So I will select the outside, type in the trim command, and I'm going to click on this portion here because I want to trim that away. Hey, it worked. Cool. This portion is also sticking outside, so I want to trim that. Right? And now I know that it sticks outside on the bottom as well, so I will select that. And where's that other piece? Is it just the one? Huh. I guess it was just that one. All right. So now, the inside is now coplanar with the outside. So now I'm going to do the opposite condition. I'm going to select the inside. And one thing that helps me doing things like this is I'll switch it to shaded view. And I will type trim. And I'm going to click in the region where I know that that trimmed area meets the top, so that when I click it, it only gets rid of that boundary there. I could go back to those just to make sure that it trimmed what I wanted it to trim. Right, that looks correct. And then I have this area over here. That looks good. And then I have bottom surface. So now what I have is a rectangular prism that has an interior, and so it's a continuous surface from inside to outside. And then what you want to do is select the inside, select the outside, join them together, and now it's just one object, right? In terms of clean modeling, this is now, should be, let me click on it just to make sure. Yeah, it's a closed poly surface. In terms of fabrication, we could 3D print it, we could mill it, we could send it to like an avionics fabricator to make this at any scale. We could reproduce these infinitely. We have what's called like the basics for a BIM construction, building information management. We don't do buildings, but that's sort of the same idea, that because the geometry is clean, we can do anything we want with it. Okay?
So the parts that were sticking out, that's where you trimmed it and then you went into it from there?
Mm-hmm. Yeah, I could probably, let me do something simpler with,
Can you use those in AutoCAD is captured, but I don't remember what the scenes were I did here. It's like the opposite of what
you could, but because the objects are not guaranteed to be clean or simple, it may not work. So I can represent that same condition with these cubes here. I use the outside to trim the inside,
USB port.
and then the inside
Do you think it's on the charger?
to trim
It's at 2%.
the outside. Then I join them together, and it's one object. Okay?
Right there, yeah. Thank you.
All right, 2.5 more steps. Wait, 1? Yeah, 2.5. I say half because the last two are kind of the same.
It's just sitting here. I think that's a good picture.
Oh, really? So, I think it might be private video.
So,
We can send you.
in terms of deliverables, this serial section step will be what you end up printing on paper. And it's very simple to do. I'm going to use the contour tool in the X, in the Y, and in the Z. And over the course of this object, I'm going to have a section cut every 2 feet. So that in the X, section cut, section cut, section cut, section cut. And the same in the Y, same in the Z. And what we will do is arrange those serial sections in, let's say, linearly from front to back, in a grid, perhaps in a direct axon, maybe in an elongated axon, exploded axon, in some way that makes sense to describe where the section cuts are taken and how they relate to the overall geometry. I'll show you how easy this actually is. So I will take our newly created continuous surface, and I'm going to use the contour command. Right? And now what the contour command asks for, what the contour command asks for is a start point and an end point of the contour vector. So I want the contours to run this way. And it's asking the distance between contours. Well, this file is in feet, and I want them to be 2 feet apart, so I can just type 2. When I hit enter, watch this. Boom, there's all my section cuts. Okay? What I'm going to do is these ones will go on the Y contour layer. Now I'm going to do it again. I'm going to do it again for the X. Select it, type in contour. The start of the contour vector and the end of the contour vector. As long as ortho is enabled, you'll get the X direction, the Y direction, and the Z direction. I'll do this. 2 is already defined. I hit enter. Boom, there's all my X sections. So I'll put this on my X contour layer. And then for the Z contours, I don't have a reliable straight up and down line that I can reference, but I can draw one. I can draw this polyline, and I can rotate it straight up. Right, so I have a straight up line. And now, when I do contour for the 3rd time, I can snap to these points to make sure that my contour vector is actually in the Z-axis. I have 2 feet between, and I hit enter. There's all my Z cuts. And I'll put that on my Z contour layer. Now, if I hide this, all of these lines are now descriptive in the X, in the Y, and in the Z of the serial sections of this object, right? The Z contours are representative of, say, if this were a building, that could be the floors. In the X contours, if this were, I don't know, some mechanical something, I don't know. But it's sections of that object going this way, and then the Y contours are sections of that object going the other way, right? And then to describe, in terms of deliverables, how this thing works, perhaps each of these section groups gets a different tone of gray. Maybe it gets a different line weight. Maybe on a section by section basis, pick one of these, right? We should have an outside line and an inside line. Right, that's what the yellow would be. Maybe when you make this diagram, each of those is a different line weight. You know, maybe everything on the inside is super thin and a medium gray, and everything on the outside is you know, a semi-medium line weight and it's black. Right? So in terms of making these serial section diagrams, you have a lot of freedom. You also so at whatever scale that is, I imagine it's probably going to be 1/16. But the way, so whatever that scale is, I haven't measured to figure out exactly what it should be. But for all of the X serial sections, draw them at a scale to where they can all fit on 113 by 19, in a grid. If there's 20 of them, then you'll have, a row of 6, a row of 5, a row of 6, or however that works out. Do the same for all the Y sections. Do the same for all the Z sections. Whatever that is, keep them at the same scale. Do you have a question? Does that make sense? My instinct, it'll probably be 1/16 inch scale to get each direction on its own page, and then we'll have one last diagram of all of them together, however you want to treat that. Okay, questions about serial sections? Okay. So the physical model is very, very, very similar to the serial sections, but it's at the scale of a physical model. So what I want to do, this is where I said I would contradict myself. Because I'm making a physical model and a physical thing, and I'm going to reference the distance of these contours based on something I can buy and that has a material thickness, I'm going to take that geometry and physically scale it down to the size that I want it to be in our tangible world. There's no way I'm going to make this thing at 20 feet by 30 feet by 40 feet. Would be fun. No way I could do it. Okay? So what I will do is select the object I created, and I'm going to export this as a separate Rhino file. I'm just going to type export, mainly because I want to change the units from feet to inches, scale it down, and not have to worry about whether or not my drawings will come out at a reasonable scale, and not be confused between which is my drawing file and which is my model file. It's good practice if you're going to make a physical model, just have a separate file. It's free, just do it. So I will call this, I already did one, so this one's different. And you're gonna save it as a final file. And I'm going to open that up. And first I'm going to move it to the origin, because I know it's way out here. I just want to move it back to the origin. Right. There it is. I want to change the units from feet to inches. Now, do I want to say yes or do I want to say no?
Yes.
Who says yes? Who says no? Okay, the answer is yes.
Yes.
The reason for that, okay, so right now it's in feet, and let's say this edge right here, it probably measures 20 feet, right? Because that was the short end of the box. If I say no, that 20 feet will now measure 20 inches. That's not a reasonable scale. That's 12 times smaller than I want it to be, and that's not the scale that I want it to be. If I say yes, it is going to convert that 20 feet to 440 inches, is that right? And it'll look like it gets bigger, but it technically measures exactly the same, just in a different unit. So if I say yes, let's say yes, looks like it got bigger, it just measures, oops, okay, 240 inches, right? Which is 20 feet, right? So now I want to scale it down, because I want to make this something that I can hold in my hand. Is anyone from the first section in here? Did we say 1/4 inch for the model? Okay, thank you. We're going to make this model at 1/4 inch equals a foot. And we're going to, so if that's the case, does anybody know how many times smaller I need to make this? Does anybody know how to figure that out? Okay, I'll show you. I'm going to erase this over here. Okay, so for every scale, there's something that's called a scale factor, and that's just how many times bigger or smaller an object is in relation to how it's being represented. Every scale factor for every scale is different, but the way that we figure that out is how many of these fit into how many of these. And that answer is our scale factor. So, how many 1/4 inches fit into 1 foot? 48. Does anybody not know how they got that answer? Just to be sure, we have, if I convert that to 12 inches, this means there are 4 of them in 1 inch. So 4 times 12 is 48. Okay? So then the scale factor is 48. that's only the scale factor for 1/4 inch. Okay? What would the scale factor be for 1/8 inch? 96. Does that make sense? We multiply this by 8 to get 1 inch, and then we multiply it by 12 to get 1 foot. So if you wanted to write that out, it would be 1 times 8 times 12, 96, right? So that means if we're going to make our model 1/4 inch, that means I need to make this 48 times smaller. And I do that with the scale command. Here you go. I scale. Let's say I scale from this corner. Well, it doesn't really matter. And the first thing it asks me for is the scale factor. I know the scale factor, but I can't type in 48. It's going to make it 48 times bigger. I'm going to have to type in 1 over 48, right? 1 over 48. Now, so small. It ends up being, let's see, 10 inches by 5 inches, more or less. Depending on your object, it might be wider, it might be smaller. But that's about the size of the model you're going to make. You're going to make this from, I think I might change the material, but what I told the last class, to keep it consistent, we're going to make it out of 1/8 inch thickness chipboard. You're going to need a laser cutter to make this model. So let's say I contour this object, and I'm going to build this model with different layers, right? The same way that we did the serial contours in the larger version. Those ones were 2 feet apart, and that was just a drawing. But if I were to cut this into layers in any direction, how far apart should those contours be? The answer is on this page. Yes. How did you get that answer?
Because if 1/4 of an inch
Has nothing to do with scale.
Then no.
That's the right answer. The reason why I would make contours 1/8 of an inch apart is because the material I'm going to make the model out of is 1/8 of an inch thick. If I were to make it out of 3/16 inch cardboard, which I might change it to, the contours would be 3/16 of an inch apart. If I were to make it out of 1 inch steel, the contours would be 1 inch apart, right? The further apart those contours are, the less resolution that we have, and then we start getting into aspects of voxelization. It's basically a 3-dimensional pixelization. We won't get into that, but that's what it's called. Okay. So what I do then is pick any direction, X, Y, or Z. If you pick X, you're going to have less sections but bigger sections. If you pick Y, you're going to have more sections but smaller sections. So they're all going to be time-consuming and frustrating, but each one will give you the resolution that we're looking for. So let's say, for example, I want my contours to run this way in the Y. So I'll type in contour. I want it to go this way. And right now it says 2, but my file is in inches, so that would be 2 inches. So I need to change that to, yes, 1/8 of an inch. I'm going to type in 0.125. Same thing. I think I could type 1/8. I've never done it that way. So those, every section is a piece of chipboard that once I lay these out flat and readable for a laser cutter, and then they get laser cut and I glue them back together, then I have a model of what I modeled, right? That's how I get what we've done from the computer into my hands. It's one way of doing it. What I can do is I can move this over here. And then what I have is at a greater resolution, because there are more of them, something that's representative of the model I'm going to get. Right? However, this very, very, very last part is probably the most time consuming. It's not hard, it's just time consuming. Okay? There is a very easy way to do it, but that involves Grasshopper, and I don't think you're ready for that. But the idea, I'll do a little bit of it. It's going to take some time, but I'll do a little bit of it to give you an idea of what you need to do. To get all of these sections readable by a laser cutter, they all need to be flat and on the same plane. And that plane should be the XY plane. So what I need to do is every single one of these sections, orient it this way and put it flat. The next one, orient it flat next to it, orient it flat next to it, next to it, next to it. Section by section by section. So like I said, going this way, you will have less sections to do, but you're going to use more material in the laser cutter because the sections are physically larger. Okay? And the way that I will lay that out is, since I need them all to be oriented in a different direction, I'll just rotate the entire thing this way first, just so that they're all at least oriented correctly. And now what I need to do is, let's say I go from the front view, right? And I select this first one. I'm going to hide this. I'm going to move this guy from where it is to 0, 0, 0. All right, there's my first one. I'm going to take my second one, and I'm also going to move it to 0, 0, 0. However, once it's there, I'm going to move it over a little bit. And I'm going to do the next one. Okay, and I'm going to keep doing that all the way along. Now, I recommend that you select your sections from either the front view or the right view, because I can't keep selecting it this way, because eventually I'm going to get to a point where there's going to be more than one line that describes that section. There could be 2 or 3 or 4, depending on how complex that interior geometry may be. I may get a section, let's say, this one right here. This is all technically one section. Right here, right? Looks like 2 lines in here. It is 2 lines, but in terms of how it looks in the top, those are those lines that describe the model at that location. Okay? Yes?
Is there any way you could flip it up and then contour it that way? Or is that just wrong?
You can contour it in any direction you want, but you only do it in one direction.
Okay, so if we flipped it up and did it like that, wouldn't they be flat already? So we wouldn't have to do that step?
Good. But you still have to separate them out, right? I can't make the model like this because there's an indefinite level of depth. I need 1 layer per section, right? So if I wanted to laser cut, this sphere sphere here, my file would probably look like this, because that describes what that looks like in each section, and how many I have is dependent on the thickness of the material I'm using. The last thing to keep in mind with this is that laser cutters are only so big. I think the ones in building 3 are 18 by 32. If you are familiar with someone named Ivan, I can try to find his contact info. He has a larger laser cutter. He's sort of just another outsourcing person to get these laser cut. Mount Sac has a makerspace. I'm sure they have laser cutters. The point is, not everybody is going to be able to laser cut here, because there's 65 of you trying to make this same model. It'll be quick, but you need to figure out in terms of schedule where to get it done and how big each manufacturer's laser cutter is. They could go up to 9 feet by 40 feet. I think is the biggest I've ever seen. Those are hard to find. But what you need to do is, let's say you were going to use the one here at school. I need to then have a rectangle that represents how big that laser cutter is. So 18 inches by 32 inches. And now every section that I peel away from the model has to fit within those bounds, depending on the complexity of the geometry, again, the thickness of the material, the direction you contour will let you know how many sheets of chipboard you need. Chipboard does not come in 18 by 32, you have to cut it down. Chipboard does come in 24 by 36, and some laser cutters are 24 by 36. So if you correctly source where you get your material from and who is going to process the material, it can leave the workload to the machine rather than you. You might end up having maybe 7 or 8 of these sheets to make this model, and I wouldn't want to physically trim 10 sheets of 24 by 36 down to 18 by 32 each. That sounds like a freaking nightmare. And what you keep all of your section cuts about 1/8 of an inch away from the outside. That's kind of just the margin of the laser cutter. It won't go all the way to the edge, but if you give yourself like 1/8 of an inch, that's pretty safe. So that means I could move these sections over here, right? And it would still be safe, and it would give me a tiny bit more room. And the closer you get them together, the more you can fit on one sheet. I would not have them touching because the laser itself has a kerf as well. I know you know what a kerf is. It's very small, but it's measurable.
What kind of file does it have to be?
A DWG. So you'll save this and then just export it as a CAD file. And then depending on who does it, they'll tell you what else they want to do. Generally, every section should be on a layer that is a red color. Usually red indicates cut. But sometimes it's yellow, sometimes it's black. It depends on the fabricator. So you have to coordinate with whomever you choose.
You were saying something about like layers, like in the middle, and I don't understand what you mean.
Well, what I meant is in the process of moving all of these layers to exist on your chipboard sheet,
Yeah.
I wouldn't select them, in the perspective view in this method.
Okay.
I would do it just layer by layer
Right.
in in opposite or in a perpendicular plane. And then you'll glue all of those sections together with super glue. Cyanoacrylate, MaxiCure. Not tacky glue, not Elmer's glue, not spray glue, not wood glue, only super glue. Don't paint them, don't sand them. When you're laser cutting them, keep track of what order they go in. If it laser cuts well, these pieces are going to fall out of your sheet, and you're gonna miss layer 45 and 47 or whatever. You can tape them down. Some fabricators will tape them down for you, and then it's just a process of first piece, glue on the second piece, glue on the third piece, glue on the fourth piece. Ideally, we would have a jig to keep these things sort of regular, but there are no regular sections to put this thing together, so you have to be very careful, very clean, very precise. If you've never built a physical model before, this is going to take you a really long time.
And this is due on Monday of 2 weeks from now?
Yes, not Monday, next Monday.
Even for the Friday class? Yeah.
Yes, because the Friday class should be here with us right now.
Just double checking.
There is a 40% chance I'm going to give you an extra week.
So we'll just come in and like the model.
I mean, you're probably going to start working on it a week before it's due, so I'll see the process in studio as you're working on it.
No, I mean like when we complete with it and it's like the due date Monday. So we're gonna like
I mean, I will check to see that it is complete in